Nothing was supposed to be down there. Then something started moving. That sentence sounds like a contradiction. A region defined by its emptiness, and yet the data showed motion where motion shouldn't be possible. Hold on to that image for a moment, because it leads us straight into one of the most surprising and instructive corners of modern astronomy. When astronomers talk about a black hole, most people picture a perfect void, a hole in space where light falls in and never comes back. That picture is useful, but incomplete. To understand why motion near a black hole is so strange, and why a detection of movement can upend our expectations, we first need a simple way to think about what a black hole really is. Imagine space-time as a stretched mattress. Put a heavy bowling ball on it and the surface curves. Roll smaller marbles nearby and they spiral in toward the central depression. That curvature is gravity in Einstein's language. Mass tells space-time how to curve, and space-time tells mass how to move. A black hole is like a bowling ball so dense it makes an almost bottomless well in that mattress. Around it things can orbit, tumble, heat up, and glow. But once anything crosses a certain boundary, the event horizon, no signal can escape back out. For distant observers, the event horizon is the last place we can hope to learn anything about what's happening nearby. It's the edge of the visible story. Visual suggestion: show an animation of a stretched mattress, a heavy ball making a deep well, and marbles spiraling inward. Audio suggestion: quiet, curious synth pad under the narration to evoke wonder. Historically, the idea of invisible massive bodies goes back farther than you might think. In the 18th century, John Michel proposed the notion of dark stars, objects so massive that even light couldn't escape their pull, an idea that was later reframed by Einstein's general theory of relativity into the modern concept of a black hole. General relativity gives us the math for how space-time bends, and how that bending creates an event horizon. But theory alone isn't enough. Observation is the referee. Over the last few decades, telescopes across the electromagnetic spectrum and clever techniques like very long baseline interferometry have let us infer black holes' presence and, in a few cases, even image their shadows. Visual suggestion: archival-style portraits of Michel and Einstein segue into real telescope imagery, then a simplified diagram of an event horizon. Audio suggestion: a subtle swell when naming historic figures to mark the weight of the ideas. So why did astronomers think nothing belonged down there? It's tempting to speak casually and say that nothing can get out of a black hole. That's not wrong, but it's a technical statement about causal structure. Signals and particles that cross the event horizon cannot reach distant observers. From Earth, that means we never see the interior. What we can see is anything that happens outside, at the rim and in the region where matter heats up and radiates as it spirals in. The darkness of the black hole's shadow is shaped by the event horizon silhouette and by light-bending effects. To the untrained eye, it appears like a perfect silent hole, but the interface between the black hole and its surroundings is often violent and luminous. Visual suggestion: contrast a pure black disk with a dynamic ring of light around it, animated light bending and photon paths. Audio suggestion: a low, sustained tone under the black disk, with higher, flickering tones as the ring brightens to communicate contrast. Now to the surprising part: telescopes registered motion where the simplest picture predicts stillness. The data weren't someone opening a door into the interior. They were patterns of light and brightness that changed over time in the very immediate neighborhood of the event horizon. One plausible observational scenario goes like this. Using high-resolution radio imaging or fast X-ray timing, astronomers saw a localized bright spot, an area of the accretion flow that flared and then moved around the black hole's shadow. In other observations, a sudden surge in light at many wavelengths hinted at a star being shredded, scattering streams of gas into eccentric orbits that then swirl and fall inward. The key is that the motion is inferred from how the light changes and where it appears to travel, all while remaining outside or exactly at the fringe of the horizon. We don't peer inside. We watch the dance just beyond the edge. Mini-hook. So if nothing escapes, how could anything move? Here's where it gets weird. The movement we detect is of matter and photons that are still outside the event horizon, behaving in extreme ways under intense gravity. Visual suggestion. Show an animated sequence of a bright spot orbiting near the edge of the shadow, intercut with a tidal stream of debris wrapping around the hole. Audio suggestion: increase tempo and brightness of music during the reveal, with a slight rhythmic pulse to convey motion. What physical processes could create the illusion or reality of motion at the edge of a black hole? Let's step through the leading explanations, from the most likely to the less likely, and why each fits the observations in different ways. First and most likely, a hotspot in the accretion disk. Accretion disks are rotating flows of gas and dust that circle black holes before falling in. The disk isn't perfectly smooth. Turbulence, shocks, and magnetic stresses can concentrate heat and brightness in localized regions. If one of those regions becomes significantly hotter or denser, it will glow brighter than the surrounding disk. Orbiting near the innermost stable circular orbit, the smallest radius where matter can orbit stably without plunging in, such a hotspot can swing around the black hole fast enough that telescopes see its light change position and brightness over short timescales. Relativistic effects complicate the picture. The side moving toward us looks brighter due to Doppler boosting, and light paths bend in ways that can make the hotspot appear to trace odd arcs. If the data show a compact bright region circling the shadow at about the timescale you'd predict for orbital motion near the ISCO, a hotspot is a clean, natural explanation. Short explanation: hotspot in the accretion disk is most likely because disks are messy and naturally produce localized flares that can orbit near the horizon. Visual suggestion: animate an accretion disk with a bright moving blob. Overlay simple labels like hotspot and ISCO. Audio suggestion: a rhythmic pulse synchronized with the hotspot's orbit to accentuate periodicity. Second, a tidal disruption event. An unlucky star gets too close and is torn apart. When a star wanders within a critical tidal radius, the black hole's gravity stretches it into a stream. Some of that stellar debris is sent outward, some falls into tight elliptical orbits and eventually forms an accretion flow that can flare dramatically. Observationally, a tidal disruption can produce a bright evolving light curve across many wavelengths, and the newly injected stream of matter can produce structures that move and precess around the black hole. TDEs are less common than disk hotspots, but when they happen they are energetic and can dominate the emission, producing strong evolving motion signatures. If the observed motion came with a multi-wavelength flare and a characteristic long decay, a tidal disruption becomes a leading contender. Short explanation: tidal disruption events are possible when observational signatures show a sudden, multi-wavelength flare with evolving brightness over days to months. Visual suggestion: show a star stretching into a stream as it approaches the black hole, then material curving into orbit and brightening. Audio suggestion: a brief dramatic crescendo during the disruption, followed by evolving melancholic tones. Third, magnetically driven plasmoids or reconnection-driven blobs. Accretion flows are threaded with magnetic fields. Magnetic reconnection, the snapping and reconnecting of field lines, can accelerate particles and launch compact blobs or jets of plasma at relativistic speeds. These blobs can appear as bright moving features at radio or X-ray wavelengths. Because magnetic activity is stochastic, it can create rapid, transient motion that looks like something is being flung outward or orbiting around the black hole. This mechanism is plausible for brief, erratic movements that don't follow a clean orbital period. Short explanation: magnetic reconnection can produce fast, bright blobs that move differently from disk hotspots. Visual suggestion: illustrate magnetic field lines wrapping the disk and then snapping, launching a bright blob. Audio suggestion: sharp percussive sounds to mark reconnection events, then a trailing bright timbre as the blob moves. Fourth, relativistic beaming and gravitational lensing effects that make stationary or slowly moving structures appear to shift. Near a black hole, light trajectories are curved, and time is stretched relative to a distant observer. A structure that is steady in the disk's frame can look like it brightens and moves because of changing beaming angles, Doppler boosting, and light bending that brings different parts of the flow into view. In some configurations, gravitational lensing of light from material behind the black hole can create apparent motions and arcs that are illusions of perspective. These optical effects can confuse simple interpretations and sometimes mimic motion even when there is little true material displacement. Short explanation: lensing and beaming can make things look like they move when geometry and relativity are at play. This is less likely to account for strong, coherent orbital signals, but very important to consider. Visual suggestion: overlay animated photon paths bending around the hole and show how the same region can appear brighter from different angles. Audio suggestion: shimmering, phase-shifted tones to suggest optical trickery. Ranking those by plausibility depends on context. If the signal is periodic and matches orbital timescales expected near the ISCO, the hotspot explanation is most likely. If the event is accompanied by a broad, sudden flare across many wavelengths, a tidal disruption moves up the list. If short, erratic bursts dominate, magnetic plasmoids are plausible. If the data show unusual apparent motion without associated material signatures, relativistic beaming or lensing could explain the illusion. Mini hook before consequences. Which of these explains the movement? The data usually let us narrow it down, but rarely do they give a single, unambiguous answer. Why does any of this matter beyond being a neat observational puzzle? First, these signals let us test gravity in the strong field regime. Einstein's equations predict specific behaviors for matter and light near an event horizon, orbital periods, redshifts, lensing patterns, that differ from simple Newtonian intuition. Observing hotspots orbiting close to the ISCO, or witnessing how an accretion flow reorganizes after a tidal disruption, gives astronomers a laboratory to check relativity where its effects are largest. Second, these events teach us about accretion physics, how matter loses angular momentum, how magnetic fields behave under extreme shear, and how particles are accelerated to near-light speeds. That feeds into broader astrophysics questions: how black holes grow, how they influence their host galaxies through jets and winds, and how the most extreme accelerators in the universe work. Visual suggestion: split screen showing theoretical predictions on one side and observational data on the other, with labeled overlays highlighting agreement or tension. Audio suggestion: a confident, hopeful musical progression to signify scientific payoff. But we also need to acknowledge limits. Telescopes measure photons in timing. They don't hand us blueprints of mechanisms. Different instruments observe different energy bands, and what looks like a clean orbit in radio might be messy or invisible in X-rays. That's why multi-wavelength campaigns are essential. Radio interferometers map the shadow scale structure. X-ray satellites catch hot inner disk physics and flares. Optical and UV telescopes follow longer-term brightening from tidal disruptions, and gravitational wave detectors can independently signal violent mergers. Combining these windows into a coordinated view is how astronomers build confidence in one explanation over another. Visual suggestion: montage of instrument logos and telescopes, EHT, Chandra, XMM Newton, LIGO, then a graphic of how data streams combine into a single timeline. Audio suggestion: layered, building textures that converge into a harmonious chord to suggest synthesis. The future looks promising. The Event Horizon Telescope is improving resolution and sensitivity. New X-ray observatories and all-sky monitors are getting better at spotting transients, and upcoming instruments will fill more spectral gaps. With faster cadence and broader coverage, scientists will be able to watch these near-horizon dramas in greater detail, catch more tidal disruption events, and possibly map the motion of hotspots well enough to measure black hole spin or the geometry of spacetime itself. Each observation peels back another layer of uncertainty. Return to the image that opened this story. Nothing was supposed to be down there. That idea still holds in a strict sense. Nothing from inside the horizon reaches us. But nothing in the sense of no activity is wrong. The neighborhood outside that boundary is one of the most active, dynamic, and extreme regions in the universe. When something starts moving in that zone, it becomes a clue, a question, and an experiment all at once. It tells us that black holes are not static tombs. They are engines of chaos and order, places where fundamental physics leaves footprints we can read if our instruments are sharp enough. Final visual and audio suggestion for the close: Fade from a still black shadow to a dynamic sequence of orbiting hotspots, flares, and data plots, then pull back to a star field with the Milky Way's center highlighted. End with a calm, resonant musical chord. If this kind of cosmic mystery lights up your curiosity, stick around. There's more. If you enjoyed this deep space detective story, please subscribe and like to keep exploring with me. And before you go, tell me in the comments which explanation you think is most likely. A burning hotspot racing around the edge, a doomed star shredded into streams, a magnetic blob on the loose, or an optical trick of light and gravity. Share this with someone who loves space mysteries, and I'll see you in the next one. Because every time something starts moving where nothing was supposed to be, the universe hands us another question worth chasing.